Okay, so hello, welcome to day 4. I'm Nicolo, one of the research fellows, and today we have Laura presenting on sequential information.
Well, thank you so much. I know that I'm neither German enough nor tall enough to pretend to be the correct one, but I guess I at least I will cover like similar things at the beginning as there will have covered, probably not.
A little hard to hear you.
Oh, I have them. How about now? No, this is bringing me back memories from MBA teaching that. Does it work? Can you guys hear me now? Okay. All right. So basically, what am I going to do? Basically, it's going to be 2 lectures on what essentially are like special cases of mechanism design. The first one will be about information design, and then the second one will be about mechanism design with limited commitment. Hopefully, by the end of the second lecture, you will see why I think that these are 2 special cases of mechanism design and how there's very deep connections between these 2. But for now, I will follow the modern econ lingo of like keeping these 2 things separate. But just to give you, okay, just to give you a sense of where the world we are going to be living in, what are the common primitives to these 2 problems? So we're going to have n agents. These are going to be players. There's going to be a finite set of states of the world. This is what's going to be representing our payoff-relevant uncertainty. And economists like to assume common priors. I should have said I'm an economist, so that like I apologize in advance. My agents will play equilibrium, and they will have common beliefs. There's a set of alternatives. And then the payoffs depend on the state of the world and these alternatives. So these are the common ingredients to both problems. And I will refer usually to these couple of ingredients: the players, the uncertainty, the common prior, the alternatives, and the payoffs as the base game. So when we think about mechanism design, what we usually do is assume that the players have some private information. And the way we represent that private information is by saying the players are going to see signals. Player 1 will see T1, player N will see Tn, and there's some relation between the signals that they see and the state of the world. And this is something that the players know, and I don't know. And then the payoffs only depend on the alternatives of that I labeled A0, not on the A1 through AM. And I'm given a mapping that says, for each realization of the state of the world, this is what I would like to obtain. And then the question is, can I design actions for the players and a way to map their actions into the outcomes, such that when the players play this game that I created for them, I implement this function pi. So this is the question in mechanism design. Can I design a game for the players such that even though they're privately informed, I will be able to convince them to play in a way that gives me the outcome that I want? So let me be even more precise. Maybe I should have, the clicker is here. So think about ad auction design. So you have one ad slot. So basically what you can do is allocate the ad slot to one of the players and ask the players for some payment. And you have a constraint that you can only allocate one ad slot. So you cannot give the ad slot to multiple players. What is the source of the private information? Basically, you can think that the set of states of the world is a product set, one for each player. And basically, each player knows their dimension of the states of the world. And this is indexing their value for the ad slot. So these players are your advertisers. And basically, what I want to implement, imagine that I'm Google, I would like to assign the slot to the advertiser that has the highest willingness to pay. Because, for instance, that would potentially mean that I can get more money from them than if I had assigned it to someone else. So basically, Google now is thinking, okay, how do I design a game so that when the advertisers are playing, they will, I can actually get the ad to go to the person that values it the most. What we're going to be doing in the first part of the lecture, which is called information design, now the perspective is a little bit different. So we have only the agents are endowed with actions. And we're given, again, a mapping that says, for each state of the world, what action profile I want to implement. And then the question is, can I find an information structure, so private information for each of the agents, such that when they play the game, so when they choose their actions under this information structure, they actually give me the outcome that I want. So instead of designing their actions, I get to design their information. So let's go back to our advertisers. Imagine that Google did their calculations, they decided the first price auction. Now they might be uncertain about what information the players might have, or if they will gain further information about their value. So now their actions are just the bids, because that's the game that they're playing a first price auction. Theta might be the common value for the ad slot. The payoffs are basically the ones in the first price auction. They get the value of the ad slot minus their payment if they win. And we're going to have, and basically this pie might be describing possible distributions over bid profiles as a function of the bidder's private information. So for instance, why would Google care about this? They might be wondering, how bad can this distribution be for them? So basically, these are the questions side by side. In mechanism design, we take as given private information and we design actions. In information design, we take as given the actions, they belong to the players, and we ask ourselves, can we design the information structure in a way that we implement a certain outcome? So that is sort of the design perspective. Either we're designing a game given an information structure, or we're designing an information structure given the base game G. But there's a flip side perspective on this, which is the one that in economics is becoming more relevant now, which is, so instead of thinking about design, I'm going to think about robustness. So I am Google and I'm thinking, what is the worst equilibrium that the players can play in? I chose the first price auction. What is the worst equilibrium that they can play? And basically this is the same as asking, we'll see that this is the same as asking, is there an information structure under which there's a very bad equilibrium that they can play? Now, the problem usually here is that to be able to do mechanism design, I need to be able to talk about the space of all mechanisms. And to do information design, I need to be able to talk about all information structures. I think this audience is more sensitive even than economists are to the fact that enumerating all these things can be very hard. So what this literature seeks to do is try to provide representations of these mechanisms and information structures in a way that is parsimonious and doesn't require this like exhaustive enumeration. So basically each of the lectures will be about talking about how do we represent information structures in the first lecture and how do we represent mechanisms in the second lecture. And by the way, you have to, like, I understand that I will probably use certain words in a different way than people use words. So please ask questions, like clarifying questions, non-clarifying questions, just interrupt me. All right. So let's start with information design. So remember, these are the things we know as analysts. We know the set of players, we know their actions, we know the payoff-relevant uncertainty, we know their payoffs, and we know that the players share a common prior. And we want to understand what is the set, but we do not know neither the information structure, which is what the players know about the state of the world, and sometimes we don't even know the extensive form that they are playing. So are they playing the prisoner's dilemma, choosing actions simultaneously? Are they playing the prisoner's dilemma, choosing actions sequentially? For the most part of the talk, I'm just going to focus on uncertainty about the information structure, fixing the extensive form. Yes.
Do we assume that there is some prior information that the agent starts from, or I guess what is the there is a common prior on the what do we know about the agents? I guess
So I'm going to do the most flexible thing, which is we don't know. So basically where the exercise is, you're going to give me a conjecture over what they can play as a function of the state of the world. And I'm going to try to find some private information structure that rationalizes what they're doing. You could imagine doing the same exercise in a world where the players already have private information, and it will look similar to what I'm going to do, but I'm just going to do the more abstract setting where I know nothing except that they share a common prior.
Are we assuming that's players that know the game?
Yes, so the players know this, they actually know the information structure. And as an analyst, I'm the one that doesn't know. So I know this, they also know this, and it's common knowledge between them, but they know the game that they are playing. So this doesn't define a game because, as Theory says, I haven't defined what the players know about theta and what they know about what other players know about theta, and so on and so forth. But they know the game that they're playing. I, as an analyst, don't know it. And yes.
And the objective is a particular fixed mapping.
Yes, so or to describe the things that are feasible and the things that are not. So basically, the idea is, how do I represent this the mappings that are consistent with equilibrium under some information structure, and the ones that are not? Because the ones that are not, then I know that there's no information structure that will incentivize the players to play in that way. So if I'm Google and I'm worried that after I chose my game, my first prize auction, then these players, nature in an adversarial way will decide their information structure, and given their information structure, they will play an equilibrium. Then this exercise will allow me to say, okay, there's some things that can never happen. So no one will bid zero. There's no information structure and everyone bids zero in the first price auction if I know that someone likes the good. So there will be a lower bound as to how bad can things be. There will be an upper bound as to how good things can be. So this is sort of the exercise. So
just give a couple of examples of what we mean by information structure. Like what are possible information?
Yes. So let's think about something very simple. So I have a seller and a buyer. The seller wants to sell 1 unit of the good to the buyer, and we know that the buyer's valuation is drawn from a common prior. So this is my theta, and I give the same notation for the prior. So you could imagine that before observing the price, and adversarial nature chooses what the buyer learns about her valuation. So, and basically one possible thing that nature could do is tell the buyer, this is your value. Reveal perfectly to the buyer the value, in which case the seller knows that nature chose to reveal the buyer the value. So when the seller chooses the price, he will do basically monopoly pricing using the prior. But you could think that another thing that nature could do is tell the buyer, look, I'm not telling you anything, so you're uninformed, in which case the seller knows the buyer is uninformed, and then the seller will just set a price equal to the expectation. So these are two extreme examples of information structures. I can make the buyer fully informed about her value. I can make the buyer I can give no information about for the buyer about the value, but the buyer understands the prior, so she knows that the expected value for the good.
So there's an assumption that nature cannot lie. How do you impose like nature can give partial information about the state of the world, but cannot give incorrect information.
Exactly. So basically, so maybe that will be more clear in the formal definition of what an information structure is. But we are always there will be two, in a sense, limitations on nature. One is that the information has to be consistent with the prior distribution. So as you were saying, nature cannot lie. And the other restriction, once we have multiple players, so here we're only disclosing information to the buyer, but if we were disclosing information to multiple players, now the multiple players, given their information, have to do something, and we're going to assume that they will play equilibrium given that information. So those are the two conditions that will limit, that will give us some bite into having a characterization of what can happen under some information structure. Because otherwise, it can become very unruly.
The second to last bullet, is this a case where the seller knows the buyer is fully informed, but the seller does not know the buyer's valuation?
Exactly.
Right. Whereas in the last one, the seller could even know the valuation, but they would still play.
No, so if the seller knew the valuation, then the seller, so you're right that if the seller knew the valuation, the total payoff will be the expectation of B. So you're right that this will be exactly the same, but here what we're saying is the seller knows, the buyer knows nothing. The only thing that the seller can do is charge the expected value. But you're right that here the payoff for the seller will be the same. Sin?
If the buyer knows that the seller knows the true value, you should accept what it is. You can have other weird methods.
Yes.
Promises to charge the true value and you get 0 AT.
Yes, the buyer is, but I think here this is a very special case where here also the buyer is getting 0 in expectation. But yes, you could elicit, you could charge a price equal to the valuation if you knew the value. So basically, if you have this case, the question is what prices are consistent with equilibrium under some information structure. I will skip this because I think we've talked enough about adversarial equilibrium selection in the auction. Just before moving on, in economics, information, sorry, yes.
Why would if the buyer does not know anything else other than the prior, why would I price the expected value? Isn't there is a asymmetry if I prefer to charge something lower because I want to get money in more cases? Oh, I guess
we're assuming here, like you can charge the expected value minus an epsilon, and the buyer will accept, and then you can make that epsilon very, very small.
And because the buyer doesn't know anything else, they are not.
Exactly. So just before moving on, and I'm missing lots of names, but in economics, this idea of the adversarial, using this tool for adversarial equilibrium selection is more common than, for instance, in OR or computer science, even though information design is being used a lot. There's I'm seeing more and more submissions to EC regarding information design. The idea in these papers is for instance, how can a platform release information about quality to get buyers to consume, or how do you release information to your Uber driver so that they take a ride, etc., etc. So there's this more like this mechanism design perspective to this problem. So I'll start being more formal so that I can answer, especially Laura's question. Let's think about the single agent example so that there is no question about the extensive form. I have one player, they move once, they are always the first and the last to move. So, and I will be using the following example just to fix ideas. The player can choose to contribute to or not contribute to fund a public good, and the value of the public good can be low or high. And there's a cost to providing this good, And the buyer, if he knew that the state is low, he doesn't want to provide this good, the good, and he does want to make the contribution if the state is high. And basically the payoffs are if the player contributes, he gets the value minus the cost and 0 otherwise. And I'm going to call mu naught the probability that the state is high, and I'm going to assume that without information, it is not optimal to contribute. So basically, that's the question that we have. What are the joint distributions over values of the public good and profiles of contribute, not contribute that are consistent with a rationality under some information structure? And to answer Theodore's question, and I think this will also address Shuchi's question, is what is an information structure is going to be a signal structure. So we're going to have a set of signals and a mapping that assigns to each state of the world a distribution over those signals. So this is like hard-coded information. So basically the idea is nature will draw the state and a signal. The player observes the signal, but not the state. The signal could be the state, so the player could learn the state. And the player knows both the prior and the signal structure. And we as analysts don't know the signal structure. And then the player decides whether to contribute. Does this make sense? So observing basically the signal, the player will update her belief about whether the public good is good or not. And then we'll choose an action to maximize her payoff. And in this case, this is basically if her posterior is sufficiently high about the state being high, then she contributes. If the posterior is sufficiently low, she doesn't contribute. There's some cutoff belief at which she's indifferent between contributing and not contributing. This is just rationality. And then when we have many players, this will be equilibrium. So given the signal structure, then I can ask myself, what is the probability under the signal structure that the player takes action A when the state is theta? And I'm just using the best response. And then I can construct my candidate P, pi, just by multiplying it by the prior, which I know as an analyst. So basically, then the question is, what are the joint distributions over actions and states of the world that I can write like this? So you can see that there's already some structure to the pies that are possible and the pies that are not. Any questions? Yes.
Sorry, can you just show us the definition of pi tilde again?
Yes, no, of course. So basically, I'm doing law of total probability. So I know, given the signal structure, now I can calculate, I know the agent's payoff, so I can calculate their best response. And that gives me the probability that under that signal structure, they take a certain action in a given state. And then when I multiply that by the prior, I have the probability of taking an action when the state is theta.
Okay, so the kind of given pi hat is really like under information.
Yes, yes. I just thought that if I wrote pi tilde of pi hat.
So you're trying to rationalize, so you're trying to find, is there a signal structure?
Exactly. So I want to find, if you give me a pi, I want to say, can I find a pi hat such that the pi that I started with is pi tilde of pi hat?
There is a trust issue here that when nature reports the pi hat, the agent trusts that this is.
Yes.
Take that as a given, or it's.
So we will take that as a given in the sense that Yes, so I will take that as given for now. There is for the single agent case, there's a whole literature in economics that's called Bayesian persuasion, where you're thinking that this pi hat is being designed by someone that is very interested in the agent's action. And there the issue of trust is very relevant because this person is designing like a single structure, releasing information, and is trying to convince me to take an action that might not be the one that I wanted to take. And then I would be more concerned about the issue of trust. But here we're just doing an exercise where like nature is metaphorical. I just don't know what the agent knows about the state of the world, and basically can summarize this by an information structure. So it's a metaphorical nature rather than a real sender. Okay, so this is just in math the set that we want to. So this I'm going to call pi mu 0 because of course this set depends on the prior. The set of these pi's that can be rationalized by some pi hats. So yes.
So you mentioned Bayesian persuasion. I always thought that were the same thing.
Hmm?
Can you walk a little bit about what's the difference between this and Bayesian persuasion?
No, mathematically these are the same,
Okay.
but I think that the question is sort of different because if I was here trying to get, I don't know, maximal contribution for the the person that's in charge of the information structure, I don't know, it's Kickstarter, and they are trying to get maximal contribution, and they are going to try to convince everyone that comes to Kickstarter that what they're saying is good. Once you think that people are trusting however you release information, the stars you give or whatnot, you can imagine that now Kickstarter has an incentive to start like putting more stars. I am going to actually, the second part of the talk will be about some sort of trust issue in mechanism design. But for now, I'm going to, instead of thinking about there's a sender that has a side agenda, I'm just using nature as a metaphor for the information structure.
Maybe you can just machine learning model, which you yourself have designed, which is giving you a signal. You trust it because you designed it.
Yes. So I'm just copying the formula so that people don't need to remember, but this already tells you some structure that any pi that is consistent with an information structure has to satisfy. The first restriction is the prior. So I know the prior. So when I take the marginal of my pi over the actions, it has to be that I match the prior. And that's in a sense that one of the restrictions that Shuchi was alluding to, which is when I'm tying nature's hands, nature cannot convince me of anything. On average, I have to know the probability of the state of the world has to be as in the prior. Ali. Because this will, when I will, in a couple of slides, I will have a property where this translates to the distribution of posterior beliefs under the information structure averages to the prior. So that's why there's the inverted quotes. And then basically, the other thing is that for every action that I take with positive probability under pi, it has to be that when that action is optimal for me. So if pi is consistent with the actions that I take under some information structure, it has to be that this is satisfied. And this comes like so that no one has to figure out. I don't know if it's obvious or if it's like immediate or not. So I'll just go for it. So I have a pi that I know that it comes from an information structure. So I'm just deriving necessary conditions. So I take my pi because it's written as pi tilde. I can sum over the state of the world. I can sum over the signals, and here I'm missing a u. So there's a u of a theta. And then basically what I do is I'll flip the way that I'm adding the state and the signals. And I'm going to multiply and divide by the total probability of observing a signal. And then if I put this probability inside here, what I have is the belief under which the action is taken. And basically, we said that when the signal is S, if the agent is taking action A, then A is the optimal action for that belief. So that means, and this holds for all these signals, because that's the action that I'm taking. So it has to be that this is better than any other action that I could have chosen. So basically, one way to think about this is that if pi is consistent with rationality, whenever pi says that I take action A should have been optimal for me. So these are just necessary conditions when we know that the pi comes from an information structure. And it turns out that these are both necessary and sufficient. So if you give me any pi that satisfies what I call the martingale property and satisfies this obedience condition, then I can find an information structure under which this is the distribution over actions and states of the world that I will obtain. And the information structure is the one that I described before, which is nature just tells the agent what to do. And maybe here, Shruchi's question will become relevant again, but basically, because nature is just metaphorical, this is a nice way of representing an information structure. I just tell the agent what to do, and the information structure will satisfy because of this condition that whenever I tell the agent to do A is what they will want to do. But this is just a representation. It's not, it's one way for us to summarize something complicated and having signals and labels, whatnot. Here's a nice set of labels. And here's a condition that pins down the signal structure. Questions? Yes. No. So basically, here the only thing I'm trying to show is that if I knew that my pi can be written as the pi tilde of some pi hat, then when I have to have that the agent prefers to do A over any other action. So basically what I did was I wrote pi using the definition of pi tilde. I changed the order of integration because I want to write here the condition that A is optimal whenever the agent sees signal S, which is this indicator function. So basically what I did was I added and subtract, I multiplied and divided by the probability of the signal so I could get the belief under which the action was taken. So basically the only thing I did was rewrite the information structure as the probability of seeing a signal, the payoffs as the probability of seeing a signal and my belief condition on that signal. And this is the payoff under which the action is optimal.
Thank you.
That's any other questions? Yes.
The structure of this is exactly similar to the structure of the dual of the Bellman equations for dynamic programming. Actually, even the proof, like you're using this inverse propensity.
Any other questions? So basically, let me just wrap up this part by saying, why do we care about this? So now we have a characterization of our set pi. It's nice of the set of pi mu naught, and it's a set of distributions that satisfy a nice system of linear inequalities. And now you could think there's a third party that's interested in whatever the agent is going to do. And if you wanted to do something like Bayesian persuasion, where you're like trying to, sorry, I'm one slide ahead. So basically you have a third party, he has some payoff that depends on the action and the state. And now we know that the payoffs that this third party can get because of the actions that the agent take can only be described by pies that satisfy our conditions. So if our third party was a designer that's in control and the agent trusts him, then he can look at our sets and say, okay, I'll look at the thing that maximizes my payoff over that set. But if we think that maybe nature is choosing what the information structure that the agent has in an adversarial way, now we can describe the minimum of the payoff of the third party in that set. And all these problems are linear programs. So the problem now has a nice structure. I don't have to be enumerating signals or anything. I'm just looking at a program that is linear in Pi with constraints. Now, given that people asked about Bayesian, one last thing is if we go back to our example, then now we can characterize our set using the payoff function for it. So basically using the martingale property, we know that we only need to characterize the probability that the agent contributes when the state is high and when the state is low. And then we can use the agent's payoffs basically to get the obedience constraint, and this gives you a condition on how frequently the agent has to contribute on the high state to be willing to contribute on the low state. And one of the reasons to put up, I had something here that is not showing up. So one of the reasons to show this figure is you can see that there's a nice duality between, so once I have the payoffs, I can give you the set of feasible distributions, but you could imagine yourself asking this a different question, which is, if I give you this and I told you, whatever the agent's payoffs are, this is the set of feasible distributions consistent with rationality, then you could imagine trying to estimate the agent's payoffs. And Vasilis Kirgianis has a paper with Edith Timmer and Drew Asiani where they're actually doing this for first price auctions. So you can use this tool to sort of flip the question. If you know Pi, can I learn you, and vice versa. Now, people were asking about Bayesian persuasion. So Bayesian persuasion it's the same as the problem that I have described, but it is using different signals. So what did we do? We got the signal from nature. We got the agent's beliefs. We determined the agent's action. And as long as the belief is above or below this threshold, then I know exactly, given the belief, what's the action that the agent took. The problem is that the belief doesn't necessarily pin the action of the agent at indifference. So in general, that's why having signals equals to actions is nicer, because you don't need to worry about how the agent is breaking ties. But if you knew how the agent is breaking ties, then you have a mapping from the agent's beliefs to the agent's actions. So you can basically think of an obedient signal structure. So you can think of implementing the same distribution over states of the world and actions, either by telling the agent what to do or telling the agent what belief he should have, where the information structure will be taken in a literal way, in the sense that if the information structure tells you mu, when you do this rule, you update to mu. So this is what this is the object that people work with in Bayesian persuasion, because they have a selection of the best responsive correspondence, which is you break ties in favor of whoever is designing the information structure. So basically what this says is that when you have a single agent, you can either recommend the agent what action to take or tell the agent the belief he should have. Both signals will work. And each approach has its downsides. The belief approach requires knowing how the agent breaks ties, but the action approach is complicated if the action space is complicated. So maybe you have a continuum of actions, but you have two states. It's better to talk about beliefs and actions. Now, these literal signal structures are Blackwell experiments. So I'm basically can think about the Blackwell experiment as inducing a distribution over posteriors, and this is where Ali's question becomes relevant, which is that if I have a literal information structure that gives me a distribution over posteriors, the distribution over posteriors is also a nice object to work with. You might wonder which are the distributions over posteriors that I might get, and it will be those that satisfy, that are consistent with the prior. So if I average out my posterior beliefs, they average out to the prior. So this is yet another way of describing these signal structures once you allow me to use beliefs as signals rather than actions. So if you are familiar with Bayesian persuasion, you do this in your sleep. But when you go to multiple agents, it will be easier to have the action characterization rather than the belief characterization. Ale. Oh, so in the actions, sorry, it's this. So in the condition that the prior puts limits as to how I can disclose information, it's this one. And when I write it in the space of beliefs, what I will get is that, so you could think of A as the probability of the belief that induces A. And that will give you that you have to average to the prior. Yes.
Simplex in the Blackbox.
Yes.
How?
Yes.
Yeah, so I'm trying to understand why that is.
Because basically, if my signal structure now takes states into distributions over posteriors. So I draw the state of the world, and then I sometimes tell you, you should believe that theta h has probability half, and sometimes theta h has to have probability 2/3. And hopefully your prior lies between a half and 2/3, because otherwise you will know that my information, it's not consistent with the prior. But you're in the other information structures, you just draw an action. Here you draw a belief. Any other questions? Okay, so just to give, I want to show you where so we've been assuming that the agent sees the signal and then takes an action that's optimal for them. I want to show you how that translates with many agents, so that I show you the hidden assumption of equilibrium in all of this. So basically now we're back to many players. We're going to start by assuming that the players take their actions simultaneously. So an information structure will be the same as before, but now I need signals for each of the players, because I might want to tell player, or nature might want to tell player 1 something that it doesn't tell player 2. So basically everything will be the same as before. The players know T1, so the players know the information structure. They observe the realization of TI. They don't observe what the others see or the state of the world, but they know, it's common knowledge that this is the information structure under which they're playing the game. And the thing is that here we could have been done with the one player case, but in the n player case, if I want to know what player I will do now, well, player I needs to think about what the others will do. So we need to close the model by saying how the players form conjectures about what the others will do as a conditional on the signals. And the assumption in this literature is that players are going to play based Nash equilibrium. So basically what the exercise is trying, so this is just a definition of BNE. So if you know Bayes-Nash equilibrium, you don't need to read this, but basically what we're going to say is that each player will choose a strategy, and a strategy is as a function of their signal, what they're going to do. And basically they're going to be best responding to the other's strategies. So they know the prior, they know the probability that their opponents are of different types given their type and each state of the world. They have a conjecture correct about what the others are doing, and it better be the case that then they don't want to deviate from the original plan. So the single agent is a nicer thing, but then basically if you give me an equilibrium, I can do the same thing again. So before here I had a pi hat, now I have psi, but again, I can ask myself, what is the probability that the agents take certain actions given the state of the world? And I can get my my joint distribution over actions and states of the world the same way I did before. Yes.
So, so you're thinking of Nash equilibrium, you're saying that's a sort of generalization of obedience.
So, well, it will, yes, it is. So this is the generalization of the optimization condition. So we said that the agent before sees the signal S and takes an action that is optimal for the updated belief. Here, I'm going to say the agent says signal TI, but in order for him to know what's optimal to do, he needs to think about what the others are going to do. And I'm going to close that with equilibrium. And you're one slide ahead because there is a definition of obedience in this setting, which is I'm going to say that the pi satisfies obedience if when I tell the agent to do AI, and he asks himself, well, what are the others doing? According to this, they're doing A minus I. And the state of the world is theta. When the agent calculates all these contingencies, on average, he prefers to do AI over AI prime. And it turns out that, so Berman, Brooks, and Morris, they define this, they define the pi's that satisfy this obedience condition and the martingale property at the prior as Bayes correlated equilibrium. So this is very similar to what we did for the single agent case, except that now I need to embed some way in which the players form beliefs about what the others are going to do. But then and if you're familiar with correlated equilibrium in non-cooperative game theory, this is this definition, but when there's only one state of the world, so the martingale property is mute. And basically the theorem in Dirk and Stephen's paper is basically a characterization of, so if a distribution over actions and states of the world can occur as an equilibrium under some information structure, if and only if it is a BC. And again, the information structure that works is you tell each player privately what they should do. And you don't tell them anything else about what the others are doing. That's not saying anything about the realism of this information structure. Is again a representation of how of what the players are doing. And again, as in the single agent case, this has, if you're maximizing over this set, you're maximizing over a set that's defined by a set of linear inequalities. So it's a nice set to work with.
In order to implement this Bayes correlated, the type of
Could you speak up? Or I can,
in order to implement this Bayes correlated equilibrium, do you need to know the type of all? Do you need to know the types of all the agents?
no. So to implement, so actually, who needs to know, the designer or the
correlating device?
So the correlating device only needs to know the state of the world. So the correlating device condition gives recommendations based on the state of the world. And again, I guess this is also related to Shuchi's question about trust. But basically, yes. So base correlated equilibrium, the correlating device can give different recommendations as a function of the state of the world. And if I didn't allow for this conditioning, this will also be a form of like blind correlated equilibrium, but it wouldn't capture all the things that players could do with private information.
I think you can formulate the same question about where agents have some prior signals.
Yes.
And there, I guess the answer is the correlating device needs to know the signals.
Yes.
Distribution of the signals that come. The correlating device will depend on.
Yes. Yes, that's a good point. So just what Kitsa was saying is that we could, and this is, I think, related also to Thor's question. If we started with a setting where I, as an analyst, know that the players already have like some signal structure, and I'm worried that they might learn more, but they already have some information, then I will be carrying here also the signals that they already have. So this fictitious nature is going to be coordinating the agents both on the basis of the state of the world, but also their signals. And there's refinements of this notion that, for instance, require nature to elicit this information from the players.
So because I'm assuming that in some cases, basically the one of the information designs that makes this feasible. What recommends, you said it recommends actions to the players.
Mm-hmm.
If the Nash equilibrium is randomized, does the mechanism recommend a distribution of her actions, or does it randomly recommend an action?
It randomly recommends an action.
Okay, and that ends up working out. There's no way to sort of back solve.
You mean, so you could be asking me two things. The one is
I guess
are their incentives will hold, but one thing that always happens is that it could be that once I ask you to do one action, you're actually different between two actions.
Okay.
And I'm assuming that you will do the one that I told you to do. Or I'm assuming nature assumes you will do what nature told you to. So there is this potential, but it's way nicer to work with recommendations on actions rather than the randomized actions, because that will give the program and the language of the signals will become much more complicated. Any other questions?
The correlated device. Like if it is not they're trying to maximize their own revenue, for example, what is
so you could think, so going back to the example that I had before, you could think that your Google, you decided you're running a first price auction. And you know the distribution from which the values are drawn, but you don't want to make more assumptions about what's the nature of how this information is distributed amongst the players. But you know that whatever the nature of that information is, they're going to play equilibrium. So now you have the characterization of this set, and now you can see how bad or good your revenue is under first price auction by calculating your payoffs over this set. So maybe you're very optimistic and you think that the players, you're a full designer, so you can control the equilibrium within the first price auction, you're going to choose the one that maximizes your revenue. But if you're thinking that for every game, for the first price auction, nature is actually trying to min-max you, you're going to go to the worst base correlated equilibrium to evaluate your payoffs from the first price auction. And in fact, Dirk and Stephen and Ben Brooks have a couple of papers trying to think about the robustness of different auctions using this methodology.
so is the this is a bit descriptive rather than descriptive, like trying to analyze the outcome of analysis rather than select or
Exactly. So this is a nice represent. So people have been doing mechanism design on the I have full control of the rules of the game for a long while, and I think that this audience is very sensitive as to how many times you're not in control. This is a tool that allows you to think about worst case scenario in a still, at least in the language that economists are more comfortable with, which is like, what are the restrictions that are imposed by a common prior and equilibrium? But now you're not in control of the information. So there are some things that you're not willing to make assumptions on. Yes, so this will be this, because you know the payoffs, you have these conditions and then you have the martingale property. And basically if you have expected utility, basically you're going to be calculating your payoffs multiplying by this, so everything will be linear in pi. Any other questions? So I have 4 minutes, which is terrible to do one more thing, but then I have a very simple example that I want to show you, because if you're thinking about adversarial nature, you might sometimes think that nature has even more power, which is to contact the player sequentially. And this is something that I work with Jeff Ely. So basically the question is, the ingredients are the same as before. Players are going to take one action, but you don't know neither how nature is disclosing information, nor how nature is contacting the players. So the players are not required to take actions simultaneously. And in particular, this means that maybe nature can give recommendations as a function of what people have done in the past. So let me show you a very simple example with no states of the world. And this is not even our example. We found it in later on. We were very happy with this example, and then later on we found it in a paper by Nishihara from 1997. So basically, this is the prisoner's dilemma. So we have the payoff from deviating is better than the payoff from both cooperating. And of course, if they both deviate, they ruin society. And I want to show you that if the payoff from being good is better than the average between deviating unilaterally and deviating jointly, then I can find an extensive form where both play cooperate with probability 1, even though they are moving once. So how am I going to do this? I'm going to flip a coin and decide who moves first. The players don't know who moves first. I'm going to contact the first mover who doesn't know that he's the first mover. I'm going to tell them to play cooperate. And if they cooperate, I'm going to tell the second player to play cooperate. And if the first player defects, I'm going to tell the second player to defect. And my claim is that under that condition, then they both cooperate with probability 1. So let's reason through this. So if you're one of the players and you hear the recommendation to defect, of course you're going to defect. You know that you're the second mover and the other guy played defect. It's a dominant strategy to play defect. And if you're being told to cooperate, well, if you follow the recommendation, because you think that the other one will follow the recommendation, you get the payoff from cooperating. And now you're thinking, what happens if I defect? Well, it could be that I'm the last person to move and I got the recommendation to cooperate, in which case the other guy cooperated, and therefore I get the good payoff from deviating. Or it could be that I'm the first one to move, in which case nature will go and tell the other person to defect. And they will defect because we just verified that. So this is the condition that I have there. Now, this says that basically I'm going to cooperate. And basically in the paper, we show that the same way that disobedient recommendation structure, information structures implement the set of all BC, then extensive forms like this with obedient recommendations are the ones that represent equilibria across a family of extensive forms. But if you're really interested, you can see that this has more power. There's no information. You just approach the player sequentially. So if you're thinking about like adversarial equilibrium selection, this nature is more adversarial than the one in BCE because it has more tools to go against the design. Okay, I'll shut up now, unless there's questions, but I'll finish the spiel.
So let's say 1 minute.
What region is achievable here under all such rules?
I don't remember it from the top of my head, but we can calculate it because we also get a linear program.
It's not just that, like, so just the conditional cost of delta is not going to be not sufficient to ensure that we can always make
No, so yes, and if this doesn't hold, you cannot get them to cooperate. Because we have some restrictions on the extensive form, so the players still have to choose their actions in a competitive way. So we don't let them, we don't allow them to write contracts in the extensive form. So I cannot say, if you cooperate, I automatically cooperate, and if you deviate, if you defect, I automatically defect. We cannot write those contracts. It's still like non-cooperative play in the extensive form. Yes, we're going to use perfect Bayesian equilibrium. And actually a big part of this paper, and that's why I'm only showing this example, and I think the other was better for presentation, is that a lot of the paper is like, how does this set changes as you go from Bayes-Nash equilibrium all the way to stronger and stronger refinements of sequential rationality.
Thank you.